Hello guys. In the previous video we did geostationary satellites. That's what we did in the previous video. And I said in this next video we're going to do the last section of gravitation, which is weightlessness. So now consider a rocket. Consider a rocket that is fixed in orbit. Consider a rocket fixed in orbit. Let's say this is our rocket. And this is our bed, and this is our lovely Mark Shuttleworth, our astronaut. This is going to be Mark Shuttleworth, our astronaut. So now, forces acting on Mark, on our astronaut, is going to be, Mark is my role model, by the way. Mark Shuttleworth, he is my role model. So yeah, that's why I had to use him as an example here. So now, as this person is lying down, the force is acting on him. Definitely there's going to be weight facing downwards towards the earth, because the earth is somewhere down here. The earth is somewhere down here, so there's going to be weight facing down like this. And there's also, since he's lying on a bed, there's going to be what? A contact force called reaction. If you remember from our forces section, we talked about contact forces, and this contact force is called reaction, normal reaction. It's represented by R. So those are the two forces that will be working on him. And this weight is also calculated as what? As mg. So W is equal to mg. So these are what? These are the total forces. Now let's calculate the resultant force. The resultant force, let's put two situations. The first situation is when Mark was still going up in space, when his rocket was still blasting off, when it was still going into space. That is situation number one. Since the rocket is going up like this, the direction that the resultant favors the direction of motion, right? We know the resultant favors the direction of motion. So since the direction of motion is up, it means all the upward forces are greater than the downward forces. That's what we know. So the forces on the astronaut upwards are greater than the forces on the astronaut downwards. So R minus mg will give us our resultant. R minus mg will give us our resultant. And by Newton's second law, Newton's second law says when you add up all the forces, no matter where they are, they should be equal to ma. Because this is what? When you're adding up forces, you get what is called the resultant. So that is the resultant. So from Newton's second law, since we have concluded that this is definitely called what? This is how we calculate the resultant. The top forces minus the bottom forces, we come up with the resultant. This will be equal to ma. That will be equal to ma. So now we are given some data. We're given some data from NASA that during launch, usually at launch, the acceleration is usually 15 g. That's what we're told by NASA. We're told that the acceleration of the rocket is usually 15 g. So our acceleration of the rocket is 15 times the acceleration of the acceleration due to gravity. That's data we are given by NASA, isn't it? Therefore, my R minus mg will be equal to m factor of 15g. With a little bit of algebra, you'll see that this R is equal to 16 mg. And what does this mean? This means that the reaction force that this person will feel, or the way the seat is pushing on him, the way Mark was feeling as he was going up into space, the seat pushing on him was 16 times mg. But what is mg? Mg is Mark's weight. Can you see? Mg is Mark's weight. So he was feeling 16 times his weight. That's the force he was feeling from his back as he was what? As he was lying on the what? On the bed during the launch. Now in orbit, that is situation number two. Situation number two, when Mark finally got to space, this is what happens when happened when Mark was in space. There is Mark in space, isn't it? And this will be the orbit. So when Mark was in space, that's the orbit. The bed was somewhere here. So I hope you can see that Mark was now floating in space. Mark was now floating in space. Let's look at the what? Let's look at okay, before he even floats, because right now you ask me, why was Mark floating? Prove that mathematically, or prove that using what? the principles of physics. Let's do that. Before Mark realized that he could float, Mark maybe saw the rocket tilting, so he went on and stood here. He went and stood here because he was what? Was shocked. He didn't know what was maybe let's just say he didn't know what was going on. So now, that is situation number 2 in orbit. He was standing here now as the rocket tilted. Let's look at the forces that are acting on him now. We have obviously the reaction force because what? Because he's standing on the or he's standing here, the contact force. And we have his what? His mg. But now I'm going to change this. I'm going to say g, acceleration due to gravity at the particular point or in that particular orbit. So I'm going to put a what? This sign here. And then this reaction, I'm going to put this reaction at the what? Is to say reaction at that particular point. Now in orbit, the acceleration of the spacecraft and the astronaut are both g. This happens, the acceleration is now g prime because there is something called free fall. There's something called free fall. So in orbit, can you see there are no rockets shooting anymore? This thing is now just in gravity, was being left in gravity. So when you leave something in gravity without adding any other force, it has the acceleration due to gravity. Like this, when I leave it like this, it falls with the acceleration due to gravity. So this rocket here, it had its acceleration due to gravity. Its acceleration was now equal to acceleration due to gravity because there were no more flames or thrust coming from the rocket. So the A was now equal to G. So let's look at our situation. Let's look at our situation here. The acceleration of the spacecraft and astronaut are both g prime in magnitude, where g prime is the acceleration due to gravity outside the spacecraft at a particular height. So this is now acceleration due to gravity at a particular height. Now for circular motion, we know for circular motion g, we have our resultant, or from Newton's second law of motion, we have what? Our resultant force. Our resultant force should be equal, should be what? Should provide that what? Should provide that force that maintains this in a circular orbit, or should be our what? Our centripetal force. That's what we know. It should be our centripetal force. So can you see the Earth is somewhere down here. So for this to maintain a circular orbit like this, it means the resultant pulling it, the forces of gravity pulling it towards this side are greater than the ones that are pulling it away from Earth for it to maintain a circular orbit like this. So which means mg is greater than r because the resultant has to be pointing in this direction towards the center for there to be circular orbit. Otherwise, the Mark wasn't going to be what? To circle Earth. So now let's do that. So which means our resultant force would have been mg prime minus the r prime. It is equal to this is now our resultant force because of what? Because of what I've explained. The circular path dictates that the circular path is like this. It dictates that the resultant force should be facing the center. Facing the center means favoring the side of the what? Of this mg now. It's not favoring the sides of mg. So it means mg must be greater than r for this side here, for the inside side, for this part here, to provide the resultant force. So resultant is my mg prime minus r prime is equal to m. But the a, since it's in free fall, the a is now g prime. So this is equal to g prime. Therefore, with a little bit of algebra, you can see that reaction force is 0 newtons. It's 0 newtons. What does that mean? When you calculate that resultant is now equal to 0 newtons, it basically means it means this astronaut Mark is weightless. Like for you to feel weight, you have to be supported by something. You have to feel the force of what? Of the floor under you. Otherwise, if you do not feel any force from the earth that is below you, you feel weightless. You don't feel anything. That is actually a property of weight. For you to feel weight, it's because the earth will be pushing against you, against your feet. When you stand on the ground like this, the only way you can feel your weight is because maybe you have mg. But it's because the earth is reacting in an opposite manner according to Newton's third law of motion. It's reacting to your feet. in an opposite and equal manner. So it will react with what? With your weight. So this is the force that you actually feel, that you feel, the reaction force. But when the reaction force is not there, you are not going to feel your weight. You see, you are not going to feel your weight because there's no more force from below your feet. So you start feeling weightless, and then now you can start to what? You can start to float. So now this guy, our Mark experiences no reaction at the floor when he walks about. At the earth's surface, we are conscious about our weight because of the reaction of the ground. That's the point I was raising. Because of the reaction of the ground, that's the only way we can be conscious of our weight. If the ground doesn't react to the presence of this mg, if we didn't react to the presence of our feet, we weren't going to feel weight, just like he's doing now. The reaction is zero, so Mark is now able to start floating. That's where you see now Mark floating in air, because there's no reaction. With this video, we have finished our gravity section, and as stated, we are going to start another topic in the next video. I hope you've enjoyed this. If you have any questions, go to the website iqmates.com. There's the group astronomy and astronomy and mechanics that I opened. So you can just ask me any question or send me a message, whatever. So yeah, this is the end of the section. See you in the next video.